Okay.
A very good day. Today we are going to use, we're going to do the lab 4, which is forced convection, and the apparatus which we are going to use is the probe, the seal, the pin, and also the fan. Right now, we have to turn on the switch, and then we have to set the power at 30 watts. And now we have to set the fan speed at 3 meters per second. Okay, dah.
Okay.
Hello, we are going to introduce the temperature, which is the temperature 1 means inlet temperature, temperature 2, which is surface temperature, and temperature from 3, probe temperature. So we are going to do the hole. Okay, we're gonna see the temperature. Okay, temperature 1. Okay. Okay, wait for the temperature change until they stabilize. Okay, we will move the second one, second hole. Okay, for the second hole, wait for the stabilize, the temperature stabilize. You can see the temperature too. Okay, we move the third hole, which is the same process. Wait until the temperature stabilize. Okay, repeat the same, the fourth hole. As usual, we wait. For the lastly, the sixth hole. As always, wait to the stabilize. Okay. Now, shut off the power before we doing the fillet fin convection.
Okay. Now we're going to measure the temperature for the fin. Yeah, fin. First, we need to set the temperature at the airflow at 3.0 ms, and then the power is for 30 watts. Okay, we take the probe, and then we measure the temperature by putting it in here from hole 1, and then like this, and then we wait for the temperature to stabilize, and then we is it and then the next one we're going to do for hole 2. That's it. Like this. Right here. Okay, we take the temperature until it stabilizes. And then we do for hole 3, 4, 5, and 6. And then take the temperature reading. Then next is hole 4. Then the next one is the fifth hole. just hold here. Okay. That's all for the fin temperature.
So after you're done with the step, you have to off the power. Then you have to take this off. Then you have to take this, switch it off. Then you have to take this off. The screw. And we change it to this one. Then we have to screw it back on. Power supply and temperature. Plug it back on. Finally, the temperature. Then we repeat what we did just now for this.
A very good day. My name is DARSHAN and my ID number is B0920103770. And today I'm going to talk on the lab for forced convection, the results, and also discussion for number 1. So for the results, this is the table for forced convection with pin surface. The heat transfer surface is the pin surface, power is 30 watts, and the air velocity is 3 meters per second. So for the probe temperature, the highest is 31.1 degrees Celsius. For the surface temperature, the highest is 42.9 degrees Celsius. For the inlet temperature, the highest is 25.8 degrees Celsius, and for the temperature difference, the highest is 7 degrees Celsius. And this is the table for forced convection with fin surface. The power output is 30 watts, and the air velocity is also the same for the previous one, 3 meters per second. For this table, the highest temperature for the probe is 37.5 degrees Celsius. For the surface temperature, the highest is 53.8 degrees Celsius. For the inlet temperature, the highest is 27.3 degrees Celsius. For the temperature difference, the highest is 10.3 degrees Celsius. That is all from my presentation. Thank you.
I'll be talking about the discussion for the chart we made for pin and fin. So according to the result we have for free convection for the pin surface, the highest of the temperature difference is 26.7 for the pin surface and free convection. So secondly, this is the fin type for the graph. The highest is 53.5 for the temperature difference. So these two are from the free convection. So from forced convection, as we can see from the graph, the third position holds the highest temperature difference, which is 7 degrees. And as you can see, compared to the free convection, it is not as linear. So the graph shows like a non-linear shape. So for the forced convection fin type, the highest temperature difference is at the 5th position, having 10.5 degrees Celsius of the temperature difference. So based on the free convection and forced convection, we can tell that the forced convection has the lower temperature difference.
Question 2. To calculate and compare the difference in gradients between free and forced convection for each surface. This is our calculations for the gradient penis surface free convections. For question 3, what can you say about the difference? Which type of convection gives us better spreads of temperature along the extended surface? For our answers, the difference shows that the finished surface has a higher temperature difference between the probe temperature and inlet temperature. This means that the finished surface is capable of absorbing more heat to its surface. This proves that finished surface gives us better spread of temperature along the extended surface. For the question number 4, the extended surface is made of stainless steel, which is relatively poor conductor. How would using aluminium or copper, a better conductor, affect the temperature gradient and the overall efficiency? For our answers for number 4, aluminium and copper has a higher thermal conductivity compared to the stainless steel. This means aluminium and copper can conduct heat better than stainless steel. So by using a better conductor, it can affect the gradient so that it become less steps, as it can transfer for heat easily, thus increasing the overall efficiency of the material.
Hello, my name is MOIRA PATERUS, and for the conclusion for our lab 4 is that the fin surface is capable of dissipating more heat, and as the gradient became less steep, the temperature difference will be increased, and the temperature along the extended surface is consistent through the convection process, and the surface area and the thermal conductivity of a material can affect the graph gradient, and the surface area and the I think I read it again. And the last one is by forcing the convection process, which in this experiment we had used a blower fan, which helped to reduce the graph gradient. And that's all from my group. Thank you.